Hey Hobby Halloween fans, welcome back to the channel. Today I'm excited to share a project that I built for a home haunter and fellow YouTuber, Van Oaks Props. Usually he makes custom props for others, but this time I'm making a custom built LED flicker controller for him to use in his graveyard display. In this video I'll walk you through the process of making this controller, starting with the design, the construction, the electronics, schematics, and Arduino code, how it's put together, and how it works. There isn't a kit available, but there's enough information in this video that potentially you could build one of these yourself. Let's start with a simple question. Why flickering LEDs? Lighting can make or break the atmosphere. Flickering LEDs mimic the look of real candlelight, creating a sense of unease and authenticity. Most store-bought flicker candles or lights only offer one type of flicker, and sometimes it's not quite what you want for your props. Maybe you want a slow pulsing glow for a prop, such as a Grim Reaper's eyes, a witch's lantern, or a rapid blinking pulse for other effects. That's where building your own controller comes in. You get to decide how the LEDs behave. After a few emails back and forth, we narrowed down the requirements for the LED flicker controller for his graveyard, and this is what we came up with. He wanted to control the speed, intensity, and the ability to run two separate flickering effects at once for different props. Additional requirements included that the installation be weather resistant for outdoor use in his graveyard, and it needed to be compatible with his existing 12-volt lighting system, making use of all his cables, lights, and power supply. In summary, these are the requirements. For the controls, I'll use two potentiometers, or pots for short, to adjust the flicker speed and brightness. Since I have two channels, I will need a total of 4 pots for this project. For weather resistance, I will use a weatherproof box like the one that Van Oaks used. To accommodate the space needed for the controls and electronics, I will use a 2-gang box. And to protect the controls, I'll use a weatherproof lid that hinges open when adjustments are needed. The electronics will be built to operate with 12-volt lighting for compatibility. Although the current graveyard display requires only a few flickering lights, the design will allow for future expansion to support up to 30 or more LED lights. I will provide screw terminals to make it easy to wire his 2-pin connectors that will integrate with the existing lighting system. For the brains of the operation, I used an Arduino microcontroller. I had a Trinket Pro in my shop that would be perfect for this project. However, I wouldn't recommend it for new builds, as I discovered a couple of things. For starters, I used to be able to program these with a micro USB cable. When that failed to even identify the board, I consulted forums and found that it was not compatible with USB 3.0. Fortunately, there was another way to program these devices. I soldered a 6-pin right-angle header and connected an FTDI serial cable for programming. However, the serial monitor for debugging purposes does not work through that cable, and the USB cable doesn't work either. I suggest that you use an up-to-date Arduino, such as an Arduino Nano. They are widely available and inexpensive on sellers like Amazon. Typically, development process begins with a breadboard prototype to establish proof of concept. However, given my extensive experience with this design and proven reliability, I can forego these initial steps and proceed directly to constructing the electronics. I have a prototype board that its dimensions are suitable for fitting within the enclosure, and I will use this board for soldering all components and circuit wiring. This proto board layout differs slightly from that of a standard breadboard, just so that you are aware of it. I use IC sockets for components that may potentially fail if they get zapped or wear out, such as the opto-isolators and the Arduino, making replacement for repair straightforward, if necessary. It is important to note that the Nano has more pins than the Trinket Pro, making them incompatible for direct substitution. So if you're doing this project with an Arduino Nano, then you need to make the necessary adjustments with the pin assignments. Here's the full schematic of the flicker controller. Feel free to pause the video and take a screenshot of it. The microcontroller is located on the left side of the schematic. This is where the 12 volts and ground connections that come into the microcontroller are made. I named the channel after the control knob colors, red and yellow, for easy distinction. The color name of the channel does not affect the types of colors of LEDs that can be connected to the channel. Any color of LED will work. These channels could have also been called A and B or 1 and 2. Analog inputs A0 and A1 are connected to the potentiometers for the red channel, with D3 serving as the corresponding output. And analog inputs A2 and A3 are connected to the potentiometers for the yellow channel, with D5 providing the output for this channel. Since the red and yellow channels differ only by their Arduino inputs and outputs, I'll explain the red channel, and the yellow channel operates the same way. Let's zoom into the red channels portion of the schematic. The pots and status indicator that are mounted on the front control panel are drawn here, on the left side of the schematic. There are two 50 k-ohm sealed potentiometers and one red LED that are wired to a 5-pin connector that connects the control panel to the circuit board. Here is a picture of the control panel wiring with the connectors. You can see that each channel has its own connector. The circuit includes 3 resistors: a 1 k-ohm resistor regulating the current to the status LED, a 220 ohm resistor controlling the current through the opto-isolator, and a 10 k-ohm resistor ensuring the MOSFET gate is properly deactivated when the opto-isolator turns off. The MOSFET I'm using can switch load currents up to 29 amps with a heatsink and can handle loads around 7 amps without the need of a heatsink. The screw terminals are the channel's output. These go to the 12-volt haunt lights in the graveyard. As a precautionary measure, there's a flyback diode across the output to prevent back EMF. While this may not be strictly necessary, it serves to enhance electrical protection. These are all the components used to make the control panel: the control knobs, pots, LEDs, panel mounts for the LEDs, and the 5-pin connectors. And this is what the assembled control panel looks like. The control panel was made from leftover masonite that I used in my haunt. I measured the position of the box's bosses to make clearance holes for them so the panel sits flush in the box. Then I located the centers of the rectangular cutouts where the electrical devices would normally be positioned and drilled the holes for the controls. Finally, I drilled holes for the protoboard standoffs. The masonite panel, front and back, was sprayed with 2 coats of polyacrylic, a clear sealer, and the front received 2 coats of a matte black spray paint. After the paint had dried, I mounted the standoffs, potentiometers, and status LEDs. I used stranded hookup wire and heat shrink tubing to solder all the connections, and hot glue to hold the pots in place and tack down the wires to complete the assembly as shown. These are all the components used to make the controller board: the Arduino and socket, the connectors that come from the control panel, resistors, diodes, MOSFETs, opto-isolators and their sockets, and screw terminals. Arranging these components on the protoboard took some trial and error. I wanted the channel electronics aligned with the connectors and the Arduino neatly in between. Then I soldered the board's electronics components, connecting them with solid hookup wire. This is what the final assembly looks like. At this stage of the project, it was time to plug in the Arduino and start coding the logic that will flicker the LEDs. This is the Arduino programming environment. The Arduino programming language is called wiring, and it is very close to C++, with a few minor differences. The requirement for this project is to have 2 flickering LED channels. It makes sense to create a class called Candle that encapsulates the flickering functionality of an LED, and then create 2 instances with that class. Here we see the 2 instances, namely Candle 1 and Candle 2. The parameters used to initialize these instances should be familiar from our schematic. Candle 1 is initialized with PWM output pin 3 and analog input A1 and A0. That's the red channel. and candle 2 is initialized with PWM output pin 5 and analog input A3 and A2. That's the yellow channel. PWM is an abbreviation for pulse width modulation. That is how we get the LEDs to be at different brightness levels. The setup function is called once when the Arduino powers on. In this function, the random number generator is seeded from reading an unused floating analog input. The idea is that a floating pin will yield random responses. The loop function is repeatedly called as long as power is applied to the Arduino. In this function, we are calling the update methods for candle 1 and candle 2. The update method is a class function that performs the random flicker algorithm. Then a short 2 millisecond delay, and that is the end of the loop function. But this function will be called again and repeat indefinitely. All the work of this program takes place inside the candle class. For those unfamiliar with classes, they're a way to encapsulate functionality. It may help to understand this concept better by analogy. You can think of a class like a cookie cutter, and an instance is each cookie made with it. One cookie cutter can produce as many cookies as needed. Some people might be tempted to call this concept a pattern or template, but those terms are already reserved for other things. Using this analogy, I've named my cookie cutter Candle with a capital C, and I have two cookie instances named Candle 1 and Candle 2. The instances are stored in memory as objects, so that would be like the dough. Now, let's look at the definition of the candle class. We declare variables that will be used in an instance. First are the pins that will be assigned. Next are the working storage that is for the brightness and speed, and these variables are for the times, to know when to change the LED brightness. This member function, called candle, is a constructor. It has the same name as the class. In our cookie analogy, this function is called when the cookie cutter is making the cookie. There are three parameters that are passed into the constructor that correspond to the specific Arduino I/O pins. LED pin is the PWM output for the channel. Brightness is an analog input where the pot is connected, and flicker pin is also an analog input with a pot. In the constructor, the pin assignments are copied to the internal variables of the instance. Then the internal variables are given their initial values. Next, the pins are configured for either input or output using pin mode. And lastly, the update function is called. This is the update member function where all of the flicker logic is located. These are the steps. Get the elapsed time in milliseconds. Read brightness pot and map it to a min and max brightness value. Read flicker speed pot and map it to a min and max flicker rate value. This check determines if the millisecond timer has wrapped around or if it's time to make a change. If not, then do nothing and just return. And if yes, we'll do the following. Pick a random time for the next flicker, scale the min and max LED brightness, calculate a flicker range, and take a random value for the noise. Add the value to the flicker brightness, but constrain it to the minimum and maximum LED value, and then write the value to the PWM output pin. The values with all capital letters are defined constants that were empirically determined through experimentation. Here at the top of the program, these are where those values are defined. These values can be changed to adjust the behavior, but they're finely tuned, so adjust with caution. It's finally time to put the controller together and show you how it works. First step, I will attach the proto board to the control panel with some M3 nuts. Next, I will plug in the 5-pin connectors from the control panel into the controller. I put a colored stripe on the edges of the connectors to key the direction of the pins that need to be plugged into the socket. The intention is for Van Oaks to attach his own wires inside the box, but for now I will connect some of my own wires for testing. I will connect them to the screw terminals, matching the color of the wire for the screw terminal color. I will install the weatherproof cable gland and pass the wires through it. On the wire ends, I will connect the barrel connectors for the power supply and the LEDs. Before I go any further, I need to perform a power on test. I will connect the 12-volt supply and see if my controller comes to life. Note that it takes about 5 seconds before the Arduino code is running, so it is normal to have this delay after turning on the power. The flickering lights are working, and they're responding to the pots. This is running perfectly. Now I will finish assembling the controller by putting the weatherproof cover on with the screws. This will hold it all together. Here's the tour of the control panel. The two channels, red and yellow, are in their own rectangular openings. At the top there's a status LED which acts like a preview of the LED flickering. It also indicates the channel output is operating as expected. The upper control knob adjusts the LED brightness level. Similar to a volume control, rotating the knob to the left decreases brightness, while turning it to the right increases brightness. The bottom control knob adjusts the flicker rate. Turning it to the left results in a slower flickering speed, while turning it to the right increases it. The objective was to translate a general requirement such as controlling brightness and flicker rate into code. The approach I took was to use this testing grid to methodically evaluate all combinations of brightness and flicker rates to empirically derive the constants in the code, and the mid position of the pots would represent the settings for an ideal candle flicker. The challenging part of this process was that the pots needed to work together in a semi-dependent manner. The brightness pot could adjust from the lowest to highest values, while the flicker needed to remain perceptible throughout that range. Finding the values and control formulas took trial and error, but I won't know if they're correct until they're installed into Van Oak Cemetery display. Now for the best part, showing you how it works. We're back at the electronics workbench where I will connect the controller to two different mini LED spotlights pointed at some miniature skulls. The red channel has a red mini spotlight aimed at this red-orange colored skull, and on the yellow channel I have a yellow mini spotlight aimed at the white skull. The camera doesn't fully capture the lighting as it appears in person, but I'll do my best to show the range of brightness and flicker speeds as clearly as possible. The LED flickering controller originated as a concept in email. It was developed using an electrical box from the hardware store, a handful of electronic components, and custom Arduino code. All that turned into something magical that can be used for creating lighting effects in haunted attractions. I will be producing additional tutorials on this channel. If you find this content valuable, please consider liking the video and subscribing to Hobby Halloween to support our growth. Also enable notifications because you don't want to miss out on the next exciting video on this channel. Thanks for watching.